Hello, my name is Chris Soulard. I'm a research geographer with the USGS in Moffett Field, California. The title of my talk today is Application of Empirical Land Cover Changes to Construct Climate Change Scenarios in Federally Managed Lands. I performed this research with Matthew Rigge from the AROS Data Center, with funding provided from the USGS Northwest Climate Adaptation Science Center and the USGS Climate Research and Development Program. This project got its start back in 2018 when I became aware of a growing body of literature using USGS back-in-time data to investigate the impact of multiple driving forces on land cover change in sagebrush landscapes. The back-in-time data are a series of fractional cover maps for different land cover types generated annually by the NLCD team. They are freely available through mrlc.gov and are now covering most of the Western United States. Around the same time that I was learning about BIT, the Climate Adaptation Science Center had a request for proposals. Almost immediately, I reached out to land managers from BLM and U.S. Fish and Wildlife Service where BIT data had been generated to discuss how BIT may be useful, not only in disentangling how climate has contributed to land cover change between 1985 and 2018, but also by projecting future land cover change based on historical climate vegetation relationships. In the end, we were funded to generate state and transition simulation models to project future land cover change with the goal of helping U.S. Fish and Wildlife Service and BLM as they develop long-term land management plans. The image to the right shows three management areas that we selected for the study: Hart Mountain National Antelope Refuge, Beaty Butte Herd Management Area, and Sheldon National Wildlife Refuge. The blue shading represents average annual precipitation between 1985 and 2018, and the smaller panels illustrate the land cover fraction for shrub, herbaceous, and bare ground cover in 2018 as mapped by BIT. Our conversation with U.S. Fish and Wildlife Service and BLM and a review of research done in the region led us to conclude that the effects of fire and invasive grasses are well understood in the study area. Knowledge regarding location and intensity of cattle and horse grazing is less complete but growing. However, the exploration of gradual change drivers like climate have received far less attention, partly because vegetation effects due to climate are typically very subtle. These changes are often hard to detect with satellite-based land cover mapping efforts. Annual back-in-time data represent a paradigm shift in land cover mapping by mapping small changes in percent cover at the Landsat pixel scale. By masking out fire and treatment footprints, we can isolate and establish climate vegetation relationships over the observed period. Empirical change rates can be directly modeled into the future as business as usual scenarios. The relative difference between the historical and projected climate can be used to adjust historical transition rates to represent climate-adjusted land cover change rates and input directly into the modeling software as a different scenario. Here is a graphical representation of our workflow. Once we compile all of our data, we performed a Pearson correlation between back-in-time percent cover and day-met precipitation and temperature data spatially at each pixel for the 1985 to 2018 period. Pixels were grouped into spatial zones of climate significance. To do this, any pixel positively correlated to both precipitation and minimum temperature were grouped into a single zone, and so forth based on every unique climate relationship. To parameterize the state and transition model, each fractional cover class for each cover type was made a state. All changes from one fractional cover class to another were made transitions. We used AdaptWest and ensemble climate models to compare projected climate to historical climate. We selected IPCC representative concentration pathway 8.5 based on the assumption that climate change would be more pronounced relative to other RCPs and that RCP 8.5 would represent the most divergent future compared to a BAU scenario. Differences were summarized for each climate correlation zone and applied as adjustment factors to alter historical transitions and create a RCP 2050 scenario. For the BAU and RCP 8.5 scenarios, we used Apex RMS software to model land cover change spatially for 3 cover types over a 32-year period, which is 2018 to 2050, across 30 Monte Carlo simulations. This was done using a 300-meter pixel resolution. Here's a closer look under the hood of Apex RMS state and transition software. On the right, states are shown as boxes, and transitions between states are reflected as arrows. If every possible transition were included for each model, we'd have nearly 5,000 unique transition combinations over 3 management units and 3 climate correlation zones, resulting in almost 136,000 possible transition targets. We narrowed this down to include a set of real transitions for each cover type based on a summary of the observed data. An example is shown below, with each row showing a unique transition target for each management unit, correlation zone, and transition. Here, the software randomly selects between the lower and upper limit for each time step. And here are our results. This plot is the average transitions between categories for the period 2018 to 2050 for the total study area, average across 30 Monte Carlo simulations. As you see, the magnitude and variability of nearly all transitions and cover types were somewhat more pronounced in the RCP 8.5 scenario compared to the BAU scenario. If you look at the circled area to the top, the amount of shrub cover at the pixel scale is increasing towards moderate shrub cover, which we categorize as shrub cover between 21 and 40% fractional cover. And if you jump to the bottom 2 grids for bare ground, the RCP 8.5 scenario has more transitions to lower percent cover as compared to the BAU scenario. But if we drill down to the management unit scale and summarize the average fractional cover for each unit over time, we find that both scenarios model a subtle decline in average bare ground in each unit, a flat to subtle increase in average herbaceous cover, and a projected increase in average shrub cover. The differences between scenarios is nearly indiscernible for bare ground and herbaceous cover, where the average fractional cover differs by 1% or less between scenarios. However, the differences are more pronounced for shrub cover, and average shrub cover is projected to differ by 2 to 5% between scenarios. Net changes from the 2018 to 2050 period for each cover type are small after averaging across management units, simulations, and considering all gains and losses by fractional cover class that are modeled simultaneously. But the examples to the right demonstrate that change slopes varied substantially over space. The red areas indicate where land cover increased, and the blue areas show where land cover decreased over the model period. A correlation analysis between change and spatial predictors suggests that cover types like bare ground increased more at high elevations. Expectedly, bare ground also increased in locations where herbaceous and shrub cover declined, and vice versa. It decreased in areas where vegetation cover is projected to become more dense. Our conclusions are not earth-shattering, but help tell the story of how climate has and will continue to shape land cover in Hart Mountain, Beaty, Butte, and Sheldon National Wildlife Refuge. If we exclude the role of fire, grazing, and invasive grasses, our projections suggest that more precipitation will promote more shrubland cover within the study area into the future. One of the conclusions that has garnered the most attention since our publication has been the nominal difference between scenarios. Our paper, which is accessible at the link at the top there, provides a range of explanations for this similarity. The most likely explanation is the climatic variability over the 1985 to 2018 reference period. The average precipitation and temperature are indeed lower over the reference period compared to RCP 8.5, but individual years over the reference period had more precipitation or a warmer minimum temperature. Upper limit change rates in the model reflect extremes during these anomalous years, and by doing so, capture much of the climate change projected by the RCP 8.5 2050 model. The short-term time horizon of the RCP 8.5 scenario is also a culprit. Had we used the year 2100 time horizon instead of the year 2050, the delta between historical and projected climate would be larger, and we would see a bigger difference between scenarios. Future refinements will include this adjustment and will also try to accommodate a larger set of change drivers to model system complexity more effectively. With that, thank you for attending. Please email me at csoulard@usgs.gov with any questions you might have.